Good morning, everybody. Welcome to another session of DSP. So, in this session, we'll be discussing regarding computational accuracy in DSP implementation. So, in this, we'll be basically discussing what are the representations which are present and how the representations can be modified in order to increase the accuracy, in order to increase the range, in order to increase the precision. So, these are just a few things to discuss around. So we'll be discussing what is meant by fixed point format, then what is meant by floating point format, what is meant by block floating point format. So how they are helpful, whether say in increasing the range or any other aspects, and what are the errors which are introduced when we are going ahead with DSP implementation. So that is what we'll be discussing in this part. So first one, number formats for signals and coefficients in DSP systems. So in this part, right, we'll be discussing regarding different number formats which are used to represent the signals and also the coefficients what you get when you're designing a DSP system. So how are these represented in the number formats or the different number formats what are utilized? So that is what we'll be discussing in this case. So in a DSP processor, what happens is generally a signal is represented. A signal is represented in a different format depending on what format you are following. If you're following a fixed format, how the signal will be represented. If you're following a floated point format, how it is represented. So these signals are represented in different numbers. So they are represented in different formats. And what happens is, since we are dealing with the processing of the signal will be passing through n number of stages. And if I assume that input is a digital and output is a digital, so whenever the system is performing some operation of this input signal, then it might be it has to represent the signal in some proper form because it is an digital representation what we are looking for. So hence, in order to represent the signal in its digital form, I have to go for different kinds of formatting. It again depends on whether you want to go for fixed point format depending on what will be the output which is intended or what is the precision is required or what accuracy is required. So it all depends on those things. So next, filter coefficients also what you have discussed in the previous session. In that we had observed that BK coefficients or AK coefficients are utilized to define the specific kind of filter. So even these are also specified in some numbers. They are specified as some numbers. So signals are also specified as numbers and filter coefficients are also specified as numbers. So how do I represent the signals and the filter coefficients in terms of some numbers? That is what we'll be discussing around in this case. Now, representation of numbers depends mainly on several aspects. So the first one, what is the range of coefficients and the signals? That is, what signal I'll be processing, what is its range, and what are the filter coefficients that in what range they fall. So if it is a low pass filter, what is the range of filter coefficients that will be expected? If it is a IIR filter, what happens to that case? So those all things matters. Now, if for example, if you're doing quantization, so if you keep n is equal to just 2 bits, so what happens is you'll be able to represent only 4 levels. So if the range is okay, that is only 4 levels are sufficient to represent a signal, then I have no issues using this. But if just 4 signals, if 4 levels are utilized and it is not sufficient, it is not able to represent the signal in proper form, if it might be possible that this might introduce the quantization errors. So if I have to reduce this, that is nothing but I am not able to incorporate the maximum range which is present, the range of the coefficients of the signals. I am not able to establish that. So what I do is I can change, I am just taking example of quantization. What I can do is I can say increase the number of bits used for quantization to be 4. So if it is 4, then I'll be having 2 raised to 4, that is 16 levels of representation. So previously only 4 levels I was able to represent, but here 16 levels. So what I have done, I have increased the range of representation for the coefficients and the signals. So that is what I can do over in this case. So whenever I'm representing the numbers with respect to the coefficients and the signals, I have to decide what is their range. So after that only I try to go ahead with what has to be done. Then what is the amount of precision required for both the cases? If you're identifying the coefficients or the signals for both the cases, what is the amount of precision required? So what does precision specify? For example, if I take an analogy, I want to measure a weight. I want to measure what is the weight of this element. Now, approximately, say I know that the weight is around, say, 10.22, 10.22 kg. So now, if I have a specific machine, say weighing machine, I'll place on this. This machine just tells me it is in kgs. Say it will tell whether it is 1 kg, 2 kg, 3 kg. It will not tell it in decimal place. So here you can see that the precision here, if the measurement device is close enough, then it will display it as 10 kg. So what is happening is you are losing this lower significant bits. So here what you're doing is the precision is reduced. In this case, I'll be able to measure a difference of 1 kg. 1.1 I cannot estimate. If it is 1.1, it might show it as 1 or it might show it as 2, depending on how the implementation goes around. So here the precision, say for this weighing machine, is in terms of kgs. So in terms of grams, it is not giving over there. In terms of kg, so 1 kg, next representation can be 2. So here it will be represented as 10 kg. So precision, what has happened? This 0.22 has been lost in this case. Suppose I have another weighing machine in which it displays as say it will display as 10.2. So here I have increased the precision. In this measuring instrument, the precision is increased. So I have a decimal place after the decimal point. So up to this accuracy or this precision, I'll be able to represent. So this is based on whether if truncation of this part is okay for you or not. That also plays an important role in deciding what number formats you will be using. What number formats. So precision also plays important role. And what is the hardware complexity which will be involved? Why hardware complexity? Because you have seen that in many of the cases, you have some repetitions also involved. That is looping constructs similar to looping constructs. For example, if you're doing convolution, so in convolution you are doing what multiplication of signal, but at the same time you are also doing some operation which is called as shifting of the signal. You're shifting the signal towards the right or left and then doing the multiplication this thing. And then what you're doing is you are adding all the things. So you're doing addition, you're doing multiplication, you're doing shifting, and it is repeated for n number of sequences. So when we're speaking of such kind of operations, hardware complexity also has to be considered. Whether the hardware supports a specific representation or not. So if that is the case, then how do I go ahead? So those all things also become important. So when we are representing the numbers. Then apart from this, speed requirements also plays an important role. Speed in the sense, suppose what happens is if you're representing signals with 2 bits, then the computational speed, let me just assume that it is 2 seconds. But if I increase the number of bits, will it affect the speed? That also I have to just check. Can I just randomly increase the number of bits which I used to represent the signal and the coefficients? So even that plays an important role. If 4 this thing is there, then whether it increases by 4 seconds or whether the computational speed still remains 2 seconds. So all depends. So again, here hardware and how the hardware is and how it basically deals with the computations. So these are the things which again decide on what representation I have to go ahead. So these are just a few things to name around when we are discussing with the representation of the numbers, which basically depend on all these parameters, that is range, precision, complexity of the hardware, and the speed requirements for say some specific applications, how it goes around. So if I'm okay with losing the precision, but I want the result fast, So I can go for different hardware which supports that, or I can adjust the representation of the numbers in that form. So this one, what this will be clear when we discuss, say, floating point numbers, a floating point representation, how speed can be improved. So there we'll discuss regarding this part. So next, let us start off with the first format, that is fixed point format. The name itself tells that the format is fixed for some particular specification. So point implies the decimal point over here. So this is the simplest one of all the formats which are available. The number is represented as an integer. The number is represented as an integer or fraction used using fixed number of bits. So what is fixed? The number of bits which are used to represent the signal or the coefficient is fixed in this case. And another point to note down is this part. A number is basically represented as an integer or a fraction, and you have fixed number of bits to do so. Then if we discuss about n-bit fixed point signed integer, how it actually appears. So we have two fixed point formats. Since we can represent it for integer and fraction, I'll be having two representations. First one, fixed point signed integer, and the other one, fixed point signed fractions. So here we can just observe for the first case. This is the fixed point format for signed integers. So here you can see that I am having a total of n number of bits in this case. So if I start from 0, 1, it is n minus 1, and this position will be, this position is n minus 2, and this position will be n minus 1. So this n minus 1 bit, if I start from this side, this n minus 1 bit will be giving me the sign, so we'll discuss regarding this in the next slide. So just simple implication is, if it is 0, it is positive. If it is 1, it has to be negative. So how this is adjusted, we can just check out. So this one represents the sign bit. So there are here, if you just see, there are n bits in total. There are n bits in total. So and the remaining part, if you just observe, it gives you the magnitude information of the integer in this case, because I am speaking of integer. So here we can just see that there is an implied binary point. There is an implied binary point. So if I write something in this form, right, there is an implied binary point in representation. Okay. So next one, how do I represent the fractions? So here you can see that if it is an integer, generally it is, say if it is a decimal number, it is 10, 11, 12, 13. So this is just an example. So in this case, if you just see, if it is an integer, it is not having any number after a decimal point. I don't have any number after the decimal point. So here, that's why the implied binary point is falling at the end of the LS bit, least significant bit. So that's why the implied binary point falls over here, since it is an integer. Now, when it is a fraction, what happens is, it might be something like this: 11.12, 12.20, something in this form. So here what happens is, here you can see that this is a number which is after the decimal point. This is a number after the decimal point. So in this case also, again, I have n number of bits. The last bit gives me the sign. If it is 1, it is negative. If it is 0, it is positive. Okay. And here you can see that these number of bits give me the information regarding the fractional part. Give me the information regarding the fractional part. Here 1.2 note down is, the implied binary point is at the first bit after the decimal. So here, for example, if I take 12, 12.11. So this decimal point, if I have to represent this number, right? So if you represent it in binary, how it will be? This one would be represented as 1100. This is 12, and this one I have to multiply it with the 2 and take the representation 0, 0. So it continues. So if I keep on multiplying, it continues. So here, this is the binary representation. So this is decimal. This is binary representation. Now, if I have to represent this number, right? How do I represent this number? So what I do is, if you just observe the representation, in this case, the implied binary is at the significant bit, most significant bit. So what I have to do is, I have to shift this to the other end and adjust the notation. So how I am doing this, we'll be discussing in the floating point representation. So when I'm doing this, what happens is, what you're doing is, suppose 12.11, if I shift this binary, what happens is, it is 0.11 into 10 raised to 2, something in this form. So this exponent again plays role in this case. So how this is adjusted? So whenever you are representing, what you're doing is you are shifting this and you're keeping this number. I cannot just represent this part. So then this number will be wrong. So what I have to do is I shift this part. So similarly, I operate it in this form. And from this implied binary point is at this location where it is specified. So immediately after the sign bit, you are just telling that you have to place a decimal point. So this one will be the first bit. So in this case, it will be like 1100, and it will continue, and it will continue. So this is how it will be represented. So this is for integer. So numbers like 1, 21, 31, wherein I don't have any decimal point. So here the implied binary will be after the least significant bit. But in this case, it will be before the most significant bit. So it is implied. You are not actually placing a dot over here. You cannot represent a dot over here. It will be a number, binary numbers. That is 1100. What we discussed, right? That will be present. So it is when you are reading it, your system will be putting an implied binary point before this based on the format how it is represented. So this is a fixed point format wherein I'm making use of n bits for the integers to representation and n bits for the fractional representation. That is numbers which are represented as fractions. So here n bit fixed point format. If we just observe what we have, how it is represented. So in this case, if you just remember how you convert your binary number to decimal number, you are just converting it to its decimal representation. So B naught into 2 raised to 0, that is the 0th bit. So B naught into 2 raised to 0, B1 into 2 raised to 1, B2 into 2 raised to 2, so on up to Bn minus 2 into 2 raised to n minus 2, and S into 2 raised to n minus 1. Now let us see what changes will be present. So that is using that binary number to represent it in decimal form. This is how it will be represented. Now, what is S? S is the sign of the number what we are considering. If it is 0, it is a positive number. If it is 1, it's a negative number. If it is 1, it's a negative number. Then what will be the range in this case? What will be the range of this format? So the range will be, since we are representing both positive and negative numbers, what will happen is I'll be able to represent numbers from minus 2 raised to n minus 1 to plus 2 raised to n minus 1 minus 1. So if, say for example, n is equal to 2, so what will be the number represented in this case? If you just observe, it is minus 2 raised to 2 minus 1, which is minus 2 raised to 1. That is, I can represent minus 2. Then up to positive numbers, minus 1, when I check, it will be 1 minus 1, which will be 1. So in when n is equal to 2, what happens? I'll be able to represent numbers from minus 2 to plus 1. I'll be able to represent only up to these numbers. So it will be minus 2, minus 1, 0, and 1. So since n is equal to 2, only 4 possibilities. So you can cross verify it in that form. Minus 2, minus 1, 0, and 1. Only 4 possibilities are present here. So that is what it implies. So when you want to represent the numbers, right, this is how it goes in. So range is minus 2 raised to n minus 1 to plus 2 raised to n minus 1 of minus 1. Then n bit fixed point fraction. So what does this imply? So if you just observe here, it is similar again as we do it for this case. So here, just one thing to remember is you have shifted the binary. So what happens is you'll be you had taken for this case you had taken what 2 raised to 0, 2 raised to 1. But after decimal place when it comes, it turns out to be 2 raised to minus 1, 2 raised to minus 2, and so on. So that is how it goes around. So here we have, so this is the decimal equivalent representation of the fractional number, which is there, which is represented in binary. So if you just start off from here, since the sign bit position is there, it is minus s into 2 raised to 0. So this is the next bit after the decimal point, implied decimal point, what we had seen in the previous line. So it is b minus 1 into 2 raised to minus 1. Then next bit weighted with 2 raised to minus 2. So on up to the last bit which is available. So this is how the representation goes around for the fraction. So again, s is the sign of the number, 0 is positive and 1 is negative. And range in this case, it will be from minus 1 to 1 minus 2 raised to minus of n minus 1. So again, if I just consider n is equal to 2, what will happen? It will be minus 1 to 1 minus 2 raised to 1 minus 2 raised to minus 1. It is 2 minus 1, it is plus 1, so minus. So it will be in that case, so it is 1 minus 1 by 2. So in this case, it will be minus 1 to 1 to half, that is 0.5. So you'll be able to represent it in that form. So that is how it goes around. Okay. So this is the range. So range plays an important role when we are discussing. So you should know what will be the range of this specific number. So now there is one problem what we can discuss in this case. So in this one, what they are asking is what is the range of the numbers that can be represented for the fixed point format using 16 bits. Using 16 bits, if the numbers are treated as signed integers and signed fractions. Signed integers and signed fractions. So in this case, what has happened? He has specified that number of bits utilized will be 16. Number of bits utilized will be 16. And what is specifying is making use of fixed point format. He is making use of fixed point format. So these two things are known to us. Now I want to know what is the range. What is the range for signed integers? So previously we saw that for signed integer, the range is minus 2 raised to n minus 1 2 plus 2 raised to n minus 1 minus 1. So when I substitute n over here, what happens is I'll be getting minus 2 raised to 15 to plus 2 raised to 15 minus 1. And when I solve it, what happens is I'll be getting this particular range. That is minus 32,768 to plus 32,767. So these are the number ranges what I'll be able to represent from minus to plus. So when n is equal to 16. Now similarly, when we consider for the assigned fractions, it was specified that it is minus 1, 2, it is minus 1, 2, 1 minus 2 raised to n minus 1. This is negative. This is negative over here. So when I substitute substitute n is equal to 16, this is what I'll be getting. And when I solve it, what happens is I'll be able to represent numbers from minus 1 to plus 0.999 up to 69485. So this is the number what I'll be able to represent. So this is the range of the numbers what I'll be able to represent in case of signed and integers and signed fractions. So next point to discuss is a double precision fixed point format. So previously we discussed regarding fixed point format. So in that we had given some details over here. So what happens in that case is there will be some fixed range which is present. So particular range will be present based on how many bits you are utilizing. Now, if I want to increase the precision, that is double the precision. So what all things come into existence? So in this case, what I'm trying to do here is double precision. So what I'm trying to increase here. So here, how do I get this double precision? One is increasing the size of the fixed point format increases the range that can be represented. So indirectly, when I'm considering the fixed point format, if I'm making use of n bits, so some particular range is there depending on whether it is integer representation or uh, floating point representation or fractional representation. So if I have to increase the range, say previously I discussed n is equal to 2, it gave me some particular range, say minus 2, say it gave me up to 1. Now if I just increase it by 1 bit, so what will be the range? Range will be minus 2 raised to 3 minus 1 to 2 raised to 3 minus 1 minus 1. So it will be 2 raised to 2, that is 4 to 3. So here you can see that what has happened when n is equal to 2, the range was minus 2 to 1. Just increase it by 1 bit. What has happened is it has changed its range from minus 4 to 3. So what you are doing is you are increasing the number of the numbers that can be represented in this particular case. So indirectly you are increasing the range. Next, doubling the size and using fixed point format gives us what is known as a double precision fixed point format. So what is the definition of double precision fixed point format? You are making use of fixed point format, but instead of using the number of bits which are n number of bits which are utilized in fixed format, what you're doing is you are doubling the size of the you are doubling the size of this format, fixed point format. So that is what you are trying to establish here. You are doubling the size, but you are doubling, and what you're doing is you are using the fixed point format. So this one gives me what is known as double precision fixed point format. Now what are the advantages in this cases when I go for double precision? So definitely range has increased. Range increases in this case, that is how many numbers I'll be able to represent. So in previous case it was minus 2 to 1, but in the other case just by 1 bit if I increased it, it is going from minus 4 to 3. So the same thing holds true even for the fractional point. The fractional representations. Now, what is the disadvantage of this case? Now, since you are doubling the size over here, what happens is, suppose you are using n bits just for the fixed point format. only the fixed point format you are using n bits. Say that is this case. Now what happens is it is having some particular range. So whenever we are implementing the computations, it will take some amount of time. But when you increase the range, it might lead to a slight increase in the computational requirements. So here, what happens, and apart from that, what would be there is you would require more storage space as compared to the fixed point format. That is single precision fixed point format. So that is what will be happening in these cases. So previous on what we discussed, it was the single precision fixed point format. If we double the size, we get the double precision fixed point format. Advantage would be the increase in the range, but disadvantage would be the storage space required be larger as compared to the single precision point format. Then what happens is when we are doing this case is suppose I want to access a number. Suppose I want to access a number from a location. So in single precision, say I'm storing it as one location. But when we double the range, what happens is one number will be stored at using two locations. So this entire thing is giving me one entire number in case of double precision. And in case of single position, only one location is sufficient for single precision. So here you are increasing the size, but at the same time, what happens is if I want to access the number which is in single precision, say for example, which is in only one location, I have to access only one memory location. But if the same bus is there, same data bus is there, and I want to access the data which is represented in double precision format, what would happen is I have to access, say here in our case, I have to access this location twice. That is one location here and one location here. That is two accesses will be present in this case. So this what is this doing? I'm assuming that the data bus size is same. So first I might fetch the least significant bit, and then I might fetch the most significant least significant information, and then the most significant information, and then overall I'll be getting the number. So here what you're doing is the access has been doubled. Then apart from that, what would happen is if you're going for multiplication and other stuff in single precision, you might require less number of cycles, machine cycles. But when you go for double precision, it might require more number of machine cycles. So when you're going for double, because more number of bits will be present over there. So that is what happens in this case. So let us wind up here, and in next class we'll be continuing with the rest of this, wherein we'll be discussing regarding say floating point representations, and then what is meant by a dynamic range, and what is meant by precision, what is meant by resolution, and lastly we'll discuss what are the errors, which are what are the method, what are the ways in which errors are introduced in DSP implementations. Thank you.